All right, does anybody have any questions unrelated to politics?
The midterm.
The midterm.
Yeah.
You're confusing me. Did I make a mistake? What's wrong?
Yeah, and you're gonna be gone from the 9th until the 13th?
No. I'm gonna be, I don't have any trips planned on the 9th, 11th, or whatever. I'm gonna be here, man. You're not getting rid of me. You're gonna have to hear me. Get angry. That guy doesn't know what he's talking about, damn dumb. People are, poor now is the same as poor in the 60s. All right. Let's go talk about Cascodes. All right, everybody's doing well on the quizzes and the homeworks? And you're getting A's? Everybody's getting A's? Is anybody, what? Oh, crap, I forgot. Did William, he turned in his stuff. Did he drop the class? Does anybody know him? All right. William, if you dropped, I noticed. Pass him around, man. All right. So let's talk about Cascode. And one more time. Everybody's good and they're able to do the calculations and the quizzes. Does anybody notice that Chrome is having some issues with opening PDFs? Let's see if it opens it here. Nope. Last class, the 221, everybody was noticing that. Yeah, but that's not Chrome, right? I think it's because I can open it in Internet Explorer. Christian. Today's homework? Yeah, today's homework. What if I can't? What if it's just too hard? Isn't it this one? I did this in the lecture. So let me comment and tell me. So what's the relationship between this current and this current? 4 times, right? So I got I and 4I, and then 4I flows through here and I calculate the VGS, and I flows through here, I calculate the VGS, and then I know that this VGS minus this VGS divided by R is this I. I did this one in class. Do you believe me? You watched the video today? Well, how can I do it again? I mean, it's... Yeah? Mm-hmm. Yeah, but here. Let's do this. Let's go here, courses, EE 420, course lecture notes, February 19th. Oh, crap. I gotta open it in a stupid window. Let's go down there and let's look. Was it this one? Oh no, this one's m equal 4. No, hold on. Here, this one. See the m here? This m is 4. And then over here, If I look, I go through and calculate with M equal I, and then I get this equation right here. There it is. All right. I don't know what to say. Oh. All right, let's talk about cascoding. I think I even said now you can do the homework on this, right? Okay, so let's talk about cascoding. So if I look at my basic current mirror and I have this, and this voltage right here, what do I want to do to keep this in saturation? What do I have to keep? What do I have to apply here?
A wider thing.
So this is a basic current mirror, same size device. What's the minimum voltage I need there?
VGS minus V threshold.
Greater than or equal to VDS sat, which is VGS minus V threshold. Anybody not remember that? I start out with the trivial questions, right, Hisham? All right, say your name. All those times I said Hickam. He's like, yeah. All right, so I go up like that. And then over here, now this is, I'm going to pause. Don't make me cry. Lucas, this is BDS. What is this voltage right here called, Lucas? What is the voltage when I enter the saturation region and I start to flatten out called? This whole voltage here is VDS. What is this voltage? VDS sat. All right, and then I'm going to ask another one. If this is where the device behaves like a current source, what is this slope? And what is that in terms of lambda? Are you reading the book? William, are you reading? Oh, he's not here. All right. Does everybody follow that? So what ideally does a current source look like? What ideally does a current source look like if I plot it in this? Straight. Boom, like that, right? Everybody got that? And if I ask, what's the output resistance of that? What's the slope of this line? 0. What's the output resistance? Infinite. Are we all getting this? We want it to behave like a current source, and then it behaves, so I go across here. Any questions? If I ask you now, quiz, and I calculate R out equals 10 meg, and I ask you if there's 20 microamps DC flowing in this side, what's the current DC flowing in this side roughly? 20 microamps. If I say R out's 10 meg and I put a millivolt at the drain, what is the current that flows? AC wise. One millivolt over 10 meg. Nobody, what was the last quiz like? Did anybody miss this? Do we have it like this on the last quiz, or is that today's quiz? There was no AC? I'm being too easy on you. All right, any questions on any of this? Mo? Nathan? Anthony? C? All right. So what do I want? I want it to be flatter. The way I do that is I use the Cascode structure. And let me just point out the name here. This is a cascade of a common grid with a common cathode. So the cascode is what it's called. No, it's Cascode. All right, spell check. Believe me, when I was writing the books, it would always flag that. Okay, it's Cascode. So here's what I'm going to do. You would agree with me, wouldn't you, that if I pin this voltage to a fixed value and I don't allow this transistor to move, that the current's going to stay relatively fixed? Yay? So here's how I'm going to do that. This is how in the rest of the current sources we're going to do the same thing. I'm just going to show you different ways of doing it. The first way and the most common way is the cascode. So what I'm going to do is I'm going to take this resistor and I'm going to run it through two gate drain connected devices. Okay? Now I'm going to run it over here like this. So I'm going to ask you, now I'm not going to ask challenging questions here. What is, let's start out with even simpler. What is that voltage? VGS. What is this voltage relative to ground? 2 VGS. What is this voltage here? I'm not messing with device sizes. By definition, VGS. And this voltage, VGS. So this voltage, I got 2 VGS here. I go downhill by a VGS. What do I have there? VGS. Everybody agree with that? All right. And if you're asked, and this you get asked all the time in job interviews, if you go for an analog job, they say, how does this work? How does the cascode current mirror work? After you draw it, you say it like this. You say you get higher output resistance by having the 2 VGS here pinning with this extra device, pins the bottom device VDS at VGS by pinning this at a known voltage. Everybody got that? And so now, what controls the current? The current is still controlled here by this VGS, still controlled by the bottom. I'm just trying to hold this VDS constant. Everybody got that? So now, what's the drawback of the cascode structure? This is the cascode. This voltage, to keep these both in saturation, has to be higher than this voltage. Okay? So now, this voltage is VDS. What's the minimum voltage I need across that transistor to keep it in saturation? VDS sat. You say, gee, you're just asking the same questions over and over again. And that's VGS plus V threshold in. Or minus V threshold. Minus V threshold in, right? So what does this voltage have to be? Or 2 VGS minus V threshold. Does everybody follow that? So you get a higher output resistance, but you have less swing. And so I want to pull up the sims from last time. where we looked at the output. Let's look at so much work. Let's look first at figure 20.28. Are there any questions before I move on? Sony? All right. Winos. You know what Winos is? You don't know what Y-N-O-S is? Let's look at that. Did you figure it out? Sony spelled backwards. See how I gotta entertain this brain up here, you know? All right, so you see here, well, wait, let's look inside here. See how crazy I am? If I look inside, I see my beta multiplier. If I go over here, I see that when I'm at the 1 volt process, at about somewhere in here, 50, 60 millivolts, I start to go into triode. Here it flattens out. Does everybody see that? And then I look and I say, okay, the output, let's figure out how to find the output resistance. Tell me what to do. One divided by the derivative of that, and it gives my output resistance about 160K. You see if I bias over here at 50 millivolts, I'm at 20K. You see if I bias up at 0.1 volts or about 40 millivolts higher, I'm at about 80K. You understand that if you change the VDS on the transistor, you can get a factor of 4 change in the output resistance, which would have a factor of 4 change in the gain we're going to find out. Everybody see that? Anywhere if I bias here, tell them way out here, the output resistance is changing all over the place. Any questions? Okay, so if you go back, everybody understands this. Now let's go look at the Cascode, which is figure 2029, the next one. Oh, finally, it's taken me dozens of hours to get it fixed, but you notice the latest version of, let's see if it's still in this one. I might have updated this since, but if you go like to chapter 2 and you go here, oh, I changed this already. He changed LT Spice. I finally got all of them. I went through all of them and fixed them. So if you have issues, download the latest LT Spice zip, okay, with the newest version of LT Spice. He did some changes and it messed with the text size and changed some of the models and all that just to torture me. All right, I'm sure it tortured everybody else too. All right, so let's go to 2029. And then notice this node here is connected over here, and this is a current source. If I push down in here, you notice that, see the gate drain connected transistor? That's providing a current mirror over to this transistor. Everybody got that? Okay, so let's go hit run. Now you remember, what was the output resistance without cascading roughly? 160, I thought, right? Something in that 100 and something, right? Yeah, so I hit run. And now I look and you see how flat the curve is out here. You see that right around this voltage, which is for this process, is the long channel process. It's the VGS is 1.05 and the VDS sat is 0.25. So this should be about 1.3 volts from the VDS sat plus VGS. See how it starts to fall off? The reason for that is this transistor, when you start going below, starts to triode. Once it starts to triode, it starts behaving like a resistor, and then you have just the output resistance of this transistor. So if you look over here, you're getting the output resistance of the bottom transistor. Now, if you lower the voltage even more, you're going to go cause the bottom transistor to triode, and you're going to get a reduction in the output resistance further. But you see out here where the cascode's operating okay, it's nice and flat. Let's find out what the difference is, and let's see what it is in this range. I'm guessing it's in the 100K range based upon our, oh wait, this is the long channel, so it's going to be higher. Let's go see what we got here. 1 over the derivative of, there we go. And you see what is, this is numerical issues here. But you see, and let's actually fix this so that it looks nice. Does everybody understand this is like picoamps oscillating back and forth? So I'm going to fix it so it looks nicer. I'm going to go 0 to, actually, let's just do logarithmic and see what it looks like. So you can see this is like a mega ohm right here. This is 10 mega ohms, 10 to the 7th ohms, and then this goes up to a giga ohm here once it hits the where both transistors are saturated. Okay, let's go do this same problem, but let's use the short channel process like we just did. And in fact, I'm sure I have a figure, but I'm going to go back and modify the this figure right here. Whoops, that wasn't right. What one was it? 27? 28? Okay, let's modify this, and let's actually first, let's run and find out what the output resistance is one more time. $160, okay. So let's do the following. I'm going to steal now I can see why people like PowerPoint. Let's move this over here. Get the scissors out. And then let's copy this. And then let's copy this and Control E it. And then let's get the wire out and wire everything together. Bothers me, I don't hear more complaining about the homework. It makes me think it's too easy. Is that the case? Bull! Yeah. I want you to be able to answer questions. All right, so I got to provide a current here. I'm going to use this source. So I'm going to do this from scratch, even though at this point, of course, I have phobias. So there we go, do that. And then let's go grab this and copy. And go over here. And then go here. And then label V bias P. And then let's copy here. See, this would be my favorite time of the class. All right, and then the model name is P_50N. N, and what were the device sizes? 100N, and what else? 5U. I don't remember, let's go see. 100N, 5U, yay, I remembered. And then let's go right click and control and show this. Does that look right to you? Christian? Giuliano? All right, let's find out. And let's see if this makes sense. This voltage is DC-wise. Oh, I don't have it. So I see the resistance is popping up right here to about 5 meg or so. If I go look at this, if I use the short channel terms just to estimate, the VGS is what? For the book, for this design, what is the VGS? Let's see. VGS 350. And what is the VDS SAT? 50. So I'm guessing around 400 millivolts, both devices go into saturation. Let's find out. That's when our resistance starts to shoot up. So I go to 400 millivolts and hey, I know what I'm doing. Goes up 400 millivolts. Does it make sense, Michael? Okay, so you see how the resistance goes up. Now, we're going to do this over and over again the rest of the semester. You see how if I'm biased here, I'm at 4 meg at 470 millivolts. If I'm biased down here at 0.4, I'm at 0.8 meg roughly. See how the output resistance changed by a factor of 5? Simply by changing millivolts across the device. This is going to get my gains to be different than what my hand calculations show because my output resistance is varying a lot. Does everybody see this? So when you go, hey, I calculated 2 meg and I got 3 meg, or I calculated a gain of 200 and I got a gain of 300. Okay, increase the VDS, show that the output resistance goes up, and then calculate or simulate the gain again. I don't want this to seem hand wavy. Okay? All right, any questions? All right, does everybody can you explain how a cascode works in simple terms? If I explain, I say, oh, all we're doing is with this extra device, we're pinning this VDS of this lower device so it doesn't vary. It tries to keep the current more stable through here. What is the drawback of using a cascode? Need a larger voltage across it. What's another drawback? More devices, larger layout area. Any questions? Now, one thing I ask you to do on tests and quizzes a lot is calculate the output resistance of a cascode. If I do that for, which I'm going to do right now, if I do that for the basic current mirror, I say, what's the output resistance? It's trivial, right? I apply a test voltage. The output resistance is the test voltage over the current, which is just R out. 1 over lambda ID. But now I'm going to do it for the cascode. It's a little bit more challenging. And I'll tell you what I'm going to do. I'm not going to look at the book. See if I can do it without looking at the book. All right. Nobody thinks that's funny. All right. You would if you were teaching the class. You'd be like, I need to look at the book. And that's fine the first few times. Make your notes. That's when I started teaching. I'd always make my notes up and I'd come in and have my notes and I'd teach, do the best I could. My first time I taught classes here at UNLV in spring of '91, it was on the 2nd or 3rd floor, whatever you want to call it, of TVE, over where there's, where the computer science area is. There was a classroom over there that's kind of like a library lab now. And they converted it into a library, but before it was a classroom. I taught EE 428, Analog and Digital Communications. It's good times. Flunked 25% of the class. It wasn't good. They didn't deserve to be there, man. I'm sorry. Yeah. Nobody's going to flunk in this class, right? Except for maybe William. All right, hopefully he didn't drop. Okay, I'm just joking, William. Don't give up on us. All right. Kinda. All right, so output resistance of the Cascode. So okay, so if I come over here, what I'm going to do is I'm going to apply a test voltage, V test, and just connect it up to VDD. So if I ask you, what is the voltage here and here, AC-wise, at the two gates? You can't see it? Oh, it was frozen? Oh. It's 0, right? So for AC, because those aren't wiggling, I'm applying the test voltage right here. So now I'm going to show you the tricks. I've done this enough so I can explain it well. This is 0, and this is 0. Everybody see that? Those AC-wise aren't wiggling. Not going to get a voltage there. Is there a DC voltage there? Gabriel? Is there a DC voltage there? Is there a DC voltage there? VGS and 2 VGS, right? There's a DC voltage. Don't freak out on me, man. Okay? This is another thing, a key to teaching. When you teach, it's better if you go in with the attitude that I'm going to lecture to these people, blah, blah, blah. Man, it's going to be boring as hell for everybody. All right? You got to kind of talk to people. Talking to people is a lot easier because you're used to doing that. Right, Victor P? All right, so notice here, what is the VGS? 0. So if the VGS is 0, what is my GM VGS of this transistor there, my voltage controlled current source? 0, it's an open. The only thing I have there is the output resistance. Looking good? Okay, so I have a current going through here. I'm going to call this IT. I've realized this is at 0, this is at 0, this is at 0. Okay? I'm going to draw, what is this AC voltage here? 0. So I have the following. I'm going to do this nice and slow. Okay, so I come down here. And then I'm going to wait to draw the transistor. I'm going to draw the output here. And I'm going to call this R out. And this output resistance is from this transistor right here. Does everybody follow? So now, I want you to realize the following. If I draw my current like this, I test. I test flows into the transistor. What flows out of the transistor? I test. Does everybody see that? So if I ask you, what is that voltage there? Okay, this is the trick to doing these problems. I test times R out. Well, wait a sec. You just told me that voltage is 0. This voltage you just told me is I test times R out. So what is this voltage here? Yeah, 0 minus I test R out. Everybody got that? So here's what I'm going to write. I'm going to write a current going down. GMN, if you want, times minus I test R out. Now I'm going to draw the output resistance here as R out. Now I'm going to sketch this nice and neat on the next page, but before I do, any questions? Yes?
Those two output resistances are the same?
Yeah, I'll just assume they're the same. You don't need to. You could call it R out 1 and R out 2 and derive it that way. Here, why don't we do that? We'll call this M1, M2, R out 1, R out 2, GMN 1, or 2 rather, GM2, whatever. Okay? Just to be a little more generic. I think I did it that way in the book. Okay, so I'm going to re-sketch it. And now, before I do, everybody understands the trick. This is 0, this is 0. I replace M1 because the VGS is 0 with a resistor. Then I note the current that leaves, I test, is equal to the current that goes through R out 1. That allows me to put this voltage as I test R out 1. Okay, and I'm going to redraw this nice and neat. So that's the one trick. The other trick's pretty straightforward. So here's my test voltage. And I'm going to ask a simpler question now. This is GM2 times minus I test R out 1. This is R out 2. And this is R out 1. This current is I test. What is the definition of the output resistance? What is it? No. The output resistance of the Cascode. That's the resistance I see looking down in there. Right, which is, let's call it R out Cascode. How about easier? This is AC, right? It's just V test over minus I test. It's minus because I've drawn it going from plus to minus instead of minus to plus. So it's a little trick. Whenever somebody asks you what's the output resistance, you apply a test voltage, and the output resistance is V over I. So if I go back here, isn't that exactly what we did? We applied a voltage. We got an AC, which is 1 volt over 10 meg. That's R out. I mean, the 1 millivolts divided by that current, if I move the 10 meg up, is R out. I'm just doing the same thing. Everybody see that? Okay, so I go back and I say, all right, got my circuit, now I need to find this. So, I'm going to do this every way, and I'm going to do this problem with different topologies, and it's going to be always the same. I can do a KCL here, or I can do a KCL here. Are they different? Nope. Exactly the same. So let's do it on the top to begin with. Okay, what's going in? And what's going out? And what's the current going through here? What's this voltage? Right? Minus? What's this voltage? All over? Yay or nay? Okay, so I'm going to move the ITs all on one side, so I get 1. Then I get plus GM R out 1. And then here, what do I get? Equals? Anybody agree with that? And any questions before I continue? No one's playing with their phones, right? Discipline, man. All right. Am I mean because I want you to pay attention? On what video was I watching today where the instructor had one of those wooden sticks? Someone was sketching in class. It made me feel bad. And they were like real good artists, and the instructor walked up and went whack right on the sketch. You know, like, that's not me, I'm nice. Yes, it is you. All right. So I get V test over I test is equal to
1 over
R out 2 plus GM R out 1, R out 2 plus R out 1. Anybody agree with that? And this, of course, is R out Cascode. What's that? Yep. So tell me, what is this approximately equal to? What can I say about GM R out 1, R out 2 relative to R out 1 and R out 2? This is way bigger than these two. The GMR out was our, what was the other name for that? What was the name that we gave in chapter 9 for GMR out? Open circuit gain. And we want that to be like hundreds, right? So if I have hundreds times an R out 1 or an R out 2, these are small. So I can write the R out Cascode is approximately GM R out squared, dropping the R out 1 and the R out 2. It's the same transistor, same bias current. Anybody follow that? So what was the output of a simple current mirror? What was the output resistance of the simple current mirror? What was R out? So simply by using Cascode, I increase the output resistance by the open circuit gain. Does everybody see that? So Cascodes are everywhere in analog design. They're used all the time. Basic current mirrors aren't used as much. They're still used, but not as much. Okay, any questions on this? Could you derive, actually I'm going to derive it for the PMOS. So I want to, if I give you a quiz and it's closed book, I want you to be able to do it, okay? So let's do it for the PMOS, and you're going to walk me through it. And I'm not going to put R out 1 and R out 2 because I don't want to spend time on that. Okay, so would everybody be okay if here's my bias. I'll just put a current source here from the beta multiplier. Tell me what to do. Find output resistance. Apply a test voltage. Now, why don't I do it a little differently this time? Let's do it so the test voltage or test current's going up like that. And then R out Cascode P is equal to what in terms of the test voltage and test current? Notice it's going from minus to plus, so this is valid. Everybody see that? Okay, so now tell me, what are my tricks? Okay, what are the AC voltages? Why don't I have the current source here?
Because the
VGS is 0, first trick. Then I come down and I look and I say that's I test, so this voltage is I test times R out P. And then I come over and I write R out P, and then I've got going down GM P times IT R out P. And that goes to looking good. And then I did a KCL right here last time connected to the source. This time I'm gonna go away and I'm gonna do the KCL right here. Doesn't matter. It's the same thing. This one it's going in, this one it's going out. Okay, so yes. Yeah. Yeah, it's going to give me a negative value. So what's leaving the node here? I test. What's leaving the node here? And then the current through here is I test R out P minus VT all over what? Looking good. So now I'm going to move the V test over here. And the ROP I'll multiply times both sides. And I'm going to skip a step and just write ROP plus GMP, ROP squared plus ROP, which is approximately GMP times R out P squared. Same thing. Any questions? We ready for something a little more exciting? Not that Cascode isn't exciting. So let me just see, make sure that I all right. Let's go look at a different Cascode. Well, wait, let's ask a different question before we go. This voltage has to be less than what? VDD minus VSG minus VSD sat. So this has to be less than. If it goes down to ground, then it works, right? But here's VDD. What is, now be careful, I'm going to ask you this, it's a little messy. What is that voltage for DC? VDD minus VSG. What is this voltage? Oh, let's ask this first. What is this voltage here? Yeah, minus 2 VSG. So what is this voltage here? And what is the minimum voltage I need across here? VDS sat. That's a, whenever I ask that, what's the minimum voltage I need between the source and the drain, or the drain and the source, your brain shuts off like mine does and goes VDS sat. That's the damn definition of it. All right? If I ask you if the MOSFET's off, how much current's flowing, the answer is 0, unless we're talking about leakage or something like that. All right. No questions. Chris. All right. Let's talk about wide swing cascodes. What does wide swing mean? Wide swing means, is that the same as before? Or is it that? Yeah, I think it was that. He has childlike amusements with things. All right. So wide swing means that I can get 2 VDS sat across the current mirror. Is anybody in CPE 301 this semester? Is anybody taking CPE 301? Was it good? Did you learn? All right. Okay, wide swing Cascode. So here's the deal. Okay, so no brainer. What do I need this voltage here to be? Yeah, I got to turn the MOSFET on, right? But what do I want this voltage to be pinned as? Why? Why do I want it to be pinned at VDS sat? So it's right on the border of triode and saturation, but then that allows this node to go all the way down to what? 2 VDS sat. Because what do I need here between the source and the drain? And here I needed VDS sat. So the question is, how do I get this pin to VDS sat? And here's how I'm going to do it. Okay, I'm going to take this current source, and when I draw this, what does everybody think? I draw this. I think that's the transistor connected to the beta multiplier that I showed in my example. It's providing the bias. And I go over here, and a diode connected that, and I just put this here. Do I need to do that? No, I could just have it straight through, but I need to develop the VGS. Everybody got that? Then I'm going to come over here. But I need, what's the voltage here? VGS. So what do I need this voltage to be? VGS plus VDS sat for the same current I and I. So I need to size this device so that it goes up a little bit and has a larger VDS sat. It has a larger VGS. So just to be clear, this device is going to be wider, it's going to be longer, and its VGS wide is going to be equal to VGS plus VDS sat. Does everybody follow that? Okay, so now, before I go any further, if you look at this I here in this VGS, I can write I equals Kp times W over L divided by 2 VGS minus V threshold N squared, and I'm just going to call this VDS sat. So this is my base device size. Does everybody follow that? Okay, now, if I take this device, it has the same current, but I'm going to make it wider, and it's going to have a larger VGS. And so what I'm going to write it as is Kp times W over L, and then I'm going to make it longer so it drops the larger voltage. So I'm going to put an X in here because I don't know how much longer I need to make it. And then I'm going to multiply that times VGS plus VDS sat minus V threshold N squared. But wait a sec, what's VGS minus V threshold N? VDS sat. So isn't this also just Kp over 2 times W over L X times 2 VDS sat squared? And to make this and this equal, couldn't I just make X equal to 4? Because if X is 4, this squared becomes 4, and they cancel, and then it goes back here. So let's go look at that. So everybody got this circuit topology memorized? Okay, let's go back and look at our example there. Or actually, did we have it open? Yeah, whatever. Let's go back here to 28. And this is the one I built. Everybody's good? And now here's what I'm gonna do. I'm gonna go get the big hand. Actually, before I do that, let me zoom out a teeny bit and let's move. And then let's take this part and let's move it over like this. Get the scissors, get the copy out, because here's my current source. Bring it over like that. And we don't need this extra label here. Get the wire, go down, boom, get the wire, boom. I'll be lazy. And then do this, and then here's what I'm gonna do. I'm gonna change this to 400. All right, looking good. Does everybody see how I made this longer? Everybody's like, I don't know about that. A little suspicious. Okay, so now I'm gonna hit run, and I'm gonna look at the current, and is it the current in here that I'm looking at? All right, that's my current. Now, a couple of things. Or actually, let's do this first. You probably can't tell if it's higher or lower resistance, right? And everybody understands I'm saying 1 over the derivative of ID, and I went over that assuming everybody follows. What is that? R out. Derivative of is the slope, and 1 over the slope is R out. So let's look at that, and I see there's my resistance. And I think it was like 160 before, now it's only like 640. Everybody see that? How can I increase the output? This is something we learned. How can I increase the output resistance of this structure so that it's higher than 720K? Pin this voltage at a higher value. This 1/4 pins it right on the border between triode and saturation. If I increase the size here, I'm going to, let's just say 1 micron, I'm going to move it out. It's not going to be able to go as low, but it's going to increase the output resistance. Let's find out. So you see what's happening there? It's going up to 0.7 meg. Now, there's some issues. So everybody sees the output resistance is going up, right? There's some issues. One is, I don't, and I'm going to do this real quick, and then when we come back next time, I'm going to go over it in more detail, all right? One is for the current in this one to match the current in this one, I need to have the drain to source voltages of this and the drain to source voltages this and the gate to source voltages the same. So I'm going to modify this basic circuit, and I'm going to do the following. And again, I'm going to go over this next time in class, so if you're like, what the hell? Don't freak out. I'm going to start out with this next time. Okay, so I'm going to go down here. Then I'm going to, in order to equalize the drain to source voltages, what I'm going to do is I'm going to copy this over like this and get the wire out. There's my wide swing. Explain to me one more time, what's the point of this one? Pin this voltage at BDS sat at a lower voltage, so I get wide swing operation. That means my output voltage can go lower. But I still need to force the current through this and generate a VGS. Here's what I'm going to do to that. I'm going to take this, I'm going to come up here, and I'm going to connect it like that. This is an incredibly common circuit in industry when you're looking at cascode structures. Okay? So now I'm going to go hit run, and I see that what I've done is I've lowered the current and I've lowered the VDS. I can increase this even more. Let's go try something even bigger and see what happens. And now I'm back up in the mega ohm range. I know you probably didn't follow that, but maybe you did. But I'm going to pick up with this when we come back on Wednesday. It would be really helpful if you read these sections in the book. So because I'm going to do another variation on this using an amplifier next time, okay, after we cover this one. So let's do our grade booster.